Hello, thanks for dropping in. I'm Alex Gardner from NASA's Jet Propulsion Laboratory, and today I'm going to talk to you about the NASA Measures project called ITSLive. And ITSLive's goal is to provide automated, low latency, global glacier velocity and elevation change data sets. And today I'm mostly going to be talking about progress we've been making with ASF and the University of Colorado Boulder and NSIDC towards the velocity product. So let's get started. So with this project, we want to provide global, standardized, low latency products of glacier change so that we can understand the processes unfolding now, but also have a long history to provide context for them. In addition to velocities, we're also producing standardized data sets of glacier elevation change and also ice shelf melt rates. And if you're interested in these, the Antarctic glacier elevation change is already available on the ITSLive website. And I'll be giving the presentation today, but this is really the cumulative work of a whole pile of clever people distributed all across the US. And so I just want to take a moment to acknowledge all of their contributions without which this work wouldn't be possible. So let's start at the beginning with the motivation. If we look at the latest report from the Intergovernmental Panel on Climate Change, the sixth assessment report, we can see that all of the climate trajectories that are likely to unfold over the next decades have us on a path to warming. And probably the most likely cases are on the higher end of the warming now, just due to inaction. And with that warming, there are consequences. And one of the largest consequences of a warming planet is rising oceans. And the oceans are rising as the temperatures warm in response to changes in land ice, surface hydrology, and the thermal expansion of the oceans. And under all scenarios, we expect a sea level rise, mean sea level rise of anywhere between a half a meter to a meter within the next century. And if we look at to the low probability, high consequence scenario where we have an instability in the West Antarctic, we could reach sea level rise exceeding 1.5 meters by the end of this century. And if we look at the individual contributors to sea level rise, you can see that it's made up by 5 basic components. Thermal expansion makes up about a third of all of sea level rise, and that's simply due to the fact that as the ocean warms, it becomes less dense and it occupies more space. We also have changes in the amount of water stored on land. So as dams fill with sediment, that extra water goes to the ocean. And also as there's increased groundwater pumping, eventually some of that water will also find its way to the ocean. But the large majority of changes in sea level come from changes in land ice, from the Antarctic ice sheet, from the Greenland ice sheet, and from glaciers, almost equally from each of the three. So if we just look at land ice alone, it accounts for about 60% of all future projections of sea level change. But if it's uncertainty that we're interested, it's a bit of a different story. Now, when we look at the sea level pie in terms of the uncertainty in each of the different components, you can see that there's a reduction in the proportional uncertainty for thermal expansion and a large increase in the proportional uncertainty for the Antarctic. And that's because of the dynamics that can unfold in the Arctic that become highly unstable and can cause rapid changes in sea level over the next century and beyond. And so it's really changes in land ice and projecting those into the future that need to be better constrained if we want to reduce uncertainty in sea level projections. And the uncertainty in ice sheet change into the future really stems from an incomplete understanding of key processes. And those key processes include land ice mechanics, so basal sliding, what is the relation between basal friction and subglacial water pressure or subglacial hydrology, calving and rifting and its relation to ice shelf stability, ice shelf thinning and its relation to ice shelf buttressing, and then bedrock topography. So knowing the elevation of the bedrock below the ice sheet is critically important to being able to model the response to a forcing. So once a forcing is incurred, it's largely the shape of the bedrock below the ice that governs the response. And then next is the exchanges of mass and energy between the ice in the atmosphere and the ice in the ocean. So this is things like precipitation, ice shelf melt by the ocean, surface melting by the atmosphere, snow, firn, and ice microphysics that governs changes in reflectance of solar radiation, and things like internal refreezing of meltwater and densification. So what we're going to talk about here is really the data sets that will help support advancing our understanding of basal sliding, ice shelf melt, calving, and rifting. And so this is looking at the strain rates of the ice sheet from space. Okay, so thinking about how we can reduce the uncertainty, it's really in understanding the response to given forcings. And this is critical and will come with in-depth and novel analysis of observations and their comparison to model simulations, and also through improved data assimilation. And one of the areas where great progress has been made is using detailed time series of surface velocity, surface elevation, to invert for parameters that we are unable to observe directly, specifically in basal parameters. And so these are just two examples of different studies that used time evolving records of ice motion to determine what was going on at the base. And another novel study that just came out recently used really high time series in situ observations of ice motion and meltwater generated to produce a model of diurnal fluctuations in glacier flow that are informed by the observations. And so it's really through model understanding of the observations and being able to see temporal variability that we can improve our understanding of the processes that need to be better understood in ice sheet modeling. So now I'm just going to talk about velocities from space. And so this is something that the It's Live project has really focused a lot of attention on. And the It's Live project has developed and uses algorithms that operate much the way your eye does. And so when you look at this image, you can clearly see that the Balturo Glacier is flowing. And this is just a stack of Landsat images. And the reason you can tell it's flowing is because the features are being advected along the surface. And It's Live uses algorithms or feature tracking that can identify the features and track them through time. And that creates records of ice flow. And we apply these methods to both radar and optical imagery. We apply it to the Landsat 8, the Landsat 9, the Sentinel-2A, Sentinel-2B, the Sentinel-1A and B, Landsat 4 and 5, and Landsat 7 data records, the full data records over all land ice. And this gives an incredibly robust picture of ice flow through time. And so here is just the representation of those satellites, and we hope to apply these same algorithms to NISAR data when it becomes available. So this is no small task. This generates huge amount of data. So just in the archive that exists today, there's about 12.5 million image pairs that need to be searched. And looking at the record as it continues into the future, there's 9,000 new image pairs to search every single day. And each image pair requires millions of template searches. So you're doing a dense search between the two images, and it generates tens of terabytes of data. And so the only way to do this is through cloud computing and distribution through the cloud. And so what I want to talk about here is really the novel architecture that ASF, JPL, and NSIDC have put together to work in this new paradigm. And so we have all of the different sensors on the left, all the different satellites, and the data that's being generated by them. And all of that data is now available on the cloud through the providers. So this is fantastic. Before, you would have had to download this data to operate on it, but now it's cloud hosted, so you can write your programs to go and access that cloud hosted data and do the processing. And so some of the data lives in Europe. So the Sentinel 2AB level 1 data is only housed in Europe. So we actually send our code over the internet to Europe, and we do all of our processing on machines in Europe. So the the machines are close to the data, and then all of the other processing is done in North America. And the image pairs are fed into our main algorithm, which is called AutoRift, and that does the dense feature tracking. And all of the data management is handled by ASS Hype 3. So there's a lot of communication and data handling that needs to happen in image pair selection, and that all happens in Hype 3. And then the data is fed back to Amazon Simple Storage Service, S3. From there, you can access it. So you can access it by a more traditional method. You can go and search the web, or you can go to a discovery notebook and actually start working with the data. And that's what I want to show you next. So here's the web address if you want to go and access the data, the image pair data via search, and then you get a link of URLs and you can download all of that data. But we're also spending a lot of effort developing cloud efficient data cubes. And so we're working with a new format called ZAR format, which is a cloud optimized gridded data format. And this allows us to do all sorts of really cool things. And so once it's implemented correctly, we can store the data on the cloud and we can rapidly access it. Here's just an example of one location for the Malaspina Glacier. There's about 30,000 image pairs that went into making this image at the bottom there. And you can see the time evolving nature of the Malaspina Glacier. And towards the end of the record, you can see that there's a surge. You can also look at that yellow point and look at the detailed time history. So you see there's strong seasonality. And then starting in about 2020, you see that the glacier started to surge and is ongoing. And the data is updated to about a month ago. So we have very short latency. It's not fully operational yet, but the architecture is there, and we just need to get the running of the machinery automated. So now I want to walk you through an example of a notebook. This is where the data really comes alive. And so what you can see here is if you go to our GitHub account, our forward-facing GitHub account, and you just click on the binder link. Now the binder is going to go and it's going to initialize your environment for you automatically. It's going to provide you with a remote machine at no cost, and it's going to open up a Jupyter Lab environment. And from there, you can double click on our notebook, open that up, and there's an overview of the notebook there and a description of how to set up your own environment. And then you can just load in the library for working with the data and create this plot on the right-hand side. Now this is a widget. There you go. I've just opened it in full screen that is going to allow you to go and select the data. So where we have these red cubes is just where our test data is available. I'm hoping that within the next month, those red cubes will be over all glaciers in the world. So you can go and select any spot. And then you can just simply click on the map and go down to the bottom right-hand corner and go create a map. You can also measure distances if you want to measure distances between the points. And right now, your virtual machine is going out, it's grabbing the data from the cloud, and it's pulling it back and generating a plot. And so you can see what's going on if you just open the log window. Tells you how long it took to go and acquire the data. And there's the plot of those 3 points. And so green corresponds to the green point on the map, orange corresponds to the orange point, and blue corresponds to the blue point. You can resize the figure. You can save it to disk, and then you can open that up, and that is a publishable quality figure that you have generated in under a few minutes. And so we're really excited about this new way of working with data, and we're really hoping that other projects will start to adopt similar approaches. And that's everything. Thanks a lot for taking the time to learn about the project. We hope that within the next month or two, that all of the global processing will be complete, and you should see some announcements on Cryolist and other places, letting you know that the data is there and accessible, and we hope that you find it useful in your research. Thank you very much.